Okay, hello everyone. I'm Weiyi Wang from Beihang University, and I'm glad to be here to share some of the ideas recently and report some of the progress in our sensitivity. Actually, this is the first time that I have come to Australia and make a talk in a foreign meeting. Yeah. So first, I want to share where we are from. We are from Beijing, and we uh, we usually take our reports at Hangzhou and Innovation City. This is today's outline. First, I would want to share some of the talk some about thermodynamic ensemble and extraordinary and practical quantum system. Thermodynamic ensemble is not only a great resource for basic physics, but also practical applications. For basic physics, it can be used for non-emission physics, exotic interaction, squeezing and teleportation, and EDM measurements, fifth force, dark matter, beyond standard model, blah blah blah. And also for practical applications, it can be used for biomag, geomagnetic prospecting, and also gyroscope for navigation. So I want to share some of the magnetometer setup in our lab. Since 2008, our lab have begun to find out the generation 1 proof of concept prototypes of first surf spin gyro in China, and we usually call this generation prototypes generation 1, and then we are now sorry, there's something wrong with my PPT. Okay, this is a generation 2, and now we are using a pulse scheme to sorry, let me find the laser. Okay, we are now using a pulse scheme to show the sensitivity, to make some research on sensitivity. And this is the generation 2.5. This is the most sensitivity in low frequency for now in our lab. And we are now developing a third generation using the multi-cell. Okay, to begin with, I would like to share review some of the basic principle. Our vapor cells contain alpha atomic spin and noble gas spin. First, the atoms are polarized by a circularly polarized polarized light, and to the excited state, and then transit back to the ground state with a different branching ratio. And then the population in the ground state is different, so make the polarization, and then the polarized alkali atomic spin will have a spin exchange collisions with nuclear spin, and so that hyperpolarized noble gas spin. And this is the way that we read out the spin information. We know that the light propagation can be described by a Maxwell equation, where the vapor cell can be regarded as a crystal that is sensitive to magnetic field or rotation, and then the polarization polarization of the light would have a rotation angle, which is proportional to polarization of the atoms, and the polarization will be sensitive to magnetic field or rotation, so that we can read out the magnetic or read out the field that we want to measure. And eigenvalue is also the most important value for sensing the atomic spin, and the real part of the eigenvalue is the relaxation rate of atomic spin, and the imaginary part is the precession, the Lamarck precession of the atomic spin. And we can see with the increase of the relaxation, the spin exchange rate, the the signal in the time domain would first become disordered and then gradually become ordered, but the sacrifice is the frequency become slowed down. Yeah. Okay. Now we will have a quick discussion on fundamental limitation. First, mean field is the practical and proven to be a great method for describing the dynamics of spin. However, here gamma is the gyromagnetic ratio of the atoms, N is the atomic density, V is the volume, T2 is the transverse relaxation time, and T is the measuring time in atomic number. But there is a question: what is the exact volume of V? There are several descriptions in this kind of in this question, like cell volume, the intersection of the pump and probe laser beams and atoms. They're quite different. So what is the exact V or N? Actually, the example is a non-uniform. So this is a question of non-uniform. So this is a typical experimental setup for the measurement of an ensemble spin. For measurement of spin, including magnetic shielding, coils, heating film, and 2 laser beams. Okay, let's see what fields are in this setup: magnetic field, thermal field, electric field, and spin field. Okay, so there are multiple physical fields coupling exist. Okay, to model this, we up assumptions, including Euler's view in fluid mechanics, coarse-grained method. This is a that means we regard we divide the whole cell into into many small volume. Each volume each volume is small enough that it can be regarded as the spin at a specific position, but large enough to include the uniform atoms. And we also assume that the atoms is in diffusion regime, and the light is well collimated, and the absorption won't change the mode of the light, the transverse mode of the light. And our research object includes single species atoms, hybrid alkali atoms, and also with noble gas with nuclear spin. Okay, we have first we employ Bloch-Terry equation by adding a diffusion term here, and this is the boundary condition where the parameter is parameterized by the average collision times for atom before depolarization. And this is actually a series of partial differential equations. Our scheme is to use a Helmholtz equation to linearize the diffusion term and perform eigenmode expansion like this. Okay. First we use the normalization and orthogonal property of eigenmode functions, and if we denote the expansion coefficient array like this, and then we will find that the formal equation would become like this, where we have assumed that the polarization along the pump direction is steady, and the solution for this is easily to be found by a linear algebra. And we have also listed the boundary condition for three kinds of cell shapes, like rectangle, cylinder, and sphere, under three kinds of common boundary conditions. Okay, and there are also other fields like pump beam, and we extend the Biot-Lambert equation into 3D case. So then it is easy to find the solution like this. But there is one special case for the field. In the case of hybrid atomic ensemble with nuclear spin, that is an effective magnetic field induced by Fermi contact interaction. We know that this field is proportional to the polarization of nuclear spin, and the effective field sensed by the electron would be proportional to the polarization of nuclear spin, and so is the nuclear spin. While there would of course there would be absorption in the pump light, so there will be a gradient in the polarization of alkali atomic spin, which will in turn lead to the gradient of the effective magnetic field. And according to the Shengdong's work, there will be a longitude magnetic gradient relaxation. And also, if there is also a gradient magnetic field, there is on classical magnetic field, then there will also be an additional magnetic relaxation rate. So also for probe light, we can show that not all the atoms in the probe light is in the vapor is detected. Only the overlap between probe light and the atoms would be probed more. So if the radius of the probe light is smaller than the vapor cell, then the whole cell will be selected. The whole cell will be selected by the mode of the probe light. So we have defined the atomic mode overlap like this. Yeah. And as for quantum noise, finally we are able to answer this. We have added a noise term in block equation to account for commutation conservation, and we perform mode analysis of noise term in a similar way, and we finally find the selected noise mode like this. The GI is the overlap contributed by the ith mode of the atoms. And for a special case, if we choose the eigenmode to be uniform, then we will obtain the mean field, the result of the mean field. So this is actually this is the evidence that the mean field method is also compatible with our method. Okay, this is the result calculated from our this is the result from our model, and polarized by the first beam, one beam, and also by two beams with a different separation. And the result is calculated like this. The blue one is the result for the blue one is the red one are the result from calculated from mean field, and the green one is our method, is calculated by our method. And as we can see that in this regime, there will be the quantum noise is very large because there are less atomic number, and at this regime there are if we increase the radius of the probe light, there will be a larger atomic number, but we see that there will be increase in at the boundary because there are smaller non-uniform because there are larger non-uniform dissipation. Then I will quickly show some of the progress in sensitivity. This is some of the setup in our experiment. This is the for heating, and this is for temperature measurement, and this is our this is the vacuum for vacuum cavity, and this is the magnetic shielding. And after several we find our setup like this, and this is the experimental setup for our whole setup, including light mechanics and electronics. And we also have a deposition of sensitivity, like vibration, light, modeling, coupling, quantum noise, and magnetic noise. And we are now, we have some progress in vibration noise at low frequency. As we know, micro vibration is equal to angular velocity input, and like this, and this would be 1 divided by f-type noise. This is also Earth position. And this is our environment. Our lab is surrounded by a river for vibration oscillation, and under the building, there is our setup, and this is a passive passive vibration isolation platform, and this is the active isolation isolation platform. Okay. This is some of the actions that we take, includes active vibration isolation and isolation platform. And this is the active vibration isolation setup, and with also with a control by particle swarm optimization, we find the isolation noise becomes much smaller. And this is the circuits. And we find that the vibration is much smaller than before. Okay, after some technical method, and then we reach our final result. Yeah. The goal for our method is that there has been fancy results in high energy regime, but for ultralight regime, there hasn't been new findings. So is it possible for finding some new physics in low energy regime? Our ultra sensitive magnetometer provides a new way for detecting them. Okay, due to time, it is due to time. I will I will pass this part. Okay, in summary, we have performed a model analysis of spin field, which is compatible with the mean field method, and we evaluate the model for multi-physical decoupling, and we also calculate the quantum noise considering spatial picking up effect. And finally, we have realized the sensitivity of 5 multiplied 10 to the power of negative 7 degree per second per hertz. And we also had some outlook in new physics and non-mission physics. This is some of our group members. Thank you.